introduction, and thanks everyone for joining my talk. Let's get started. So, my name is Hao, and it's super excited to be invited to ODSC with us to share our recent development on open source LLM serving system. So, just a little bit more background about myself. So, I'm currently an assistant professor at UC San Diego, and I work a lot in open source large language models and the related software system stack. Okay, so for today's talk, we are going to spend 30 minutes talk about some really useful distributed system details about how to serve today's large language models. But before that, I'd like to spend a few minutes to share our interesting journey in the past 6 months in developing the very famous open source model called Vicuna and the evaluation platform called Chatbot Arena. Yeah, let's get started. So the story begins, of course, since Meta generously made their Llama models open source this March to the public. And since its release, the open source large language model development become very, very active. And we can almost observe daily updates even today. And out of curiosity, we requested access to the Llama weights and started playing with the open source Llama model. The original Llama model were just plain large language models, which means that they seems very strong in many benchmarks, but not that useful. So for example, they cannot actually precisely follow human instructions pretty well. And meanwhile, we discovered a very nice website called ShareGPT. And this is an online website where people install a Chrome extension and start sharing their favorite conversations with ChatGPT online. And actually today, I think OpenAI also has a similar feature. We started thinking about why don't we just use ShareGPT data to fine-tune Llama. So we basically crowd all the data in ShareGPT early this March, and putting things together, a lot of interesting things happen. So we by fine-tuning the Llama model using the ShareGPT data, we immediately got the Vicuna model. And the really interesting part about this Vicuna model is that after we obtain a model, we really don't know whether it is a good model or not. Because it is basically a random product of two unrelated things, right? One is a Llama weight, the other is a random data set that we found online. So we just deploy Vicuna and let many users try these models. And we start realizing a very, very surprising phenomenon. So we find that on one hand, Vicuna is strongly preferred over its baseline models, Llama, by most of our users who ever tested it. So a lot of users are surprised that Vicuna performs so similarly to ChatGPT. But on the other hand, when we use some very rigorous academic benchmark to evaluate the early versions of Vicuna we trained, we found that they do not improve or sometimes can even decrease those benchmark numbers like generated by the NLP community. So this slide shows an example where a prompt question is answered by two chatbot assistants in a multi-turn dialogue. And despite both models are actually giving the right answers, Assistant B's answer is often preferred by users because of its stronger instruction following ability and more detailed explanation, and also the style of these answers, and some other like very, very subtle language-related nuances. And this phenomenon suggests that there is a fundamental discrepancy between user perceptions of the usefulness of this kind of like chatbot assistance and the criteria adopted by conventional NLP benchmarks. So this drives us to think about the question, so how can we evaluate human preference of today's strong chatbots? And this answer is quite obvious, right? So the gold standard to evaluate human preference is apparently to ask human to rate these chatbots. So following this intuition, we start thinking about like, how can we quickly connect human votes or say human preference to rank these chatbots. So apparently this isn't a cheap and easy process. As you can see, LLM companies like OpenAI and Anthropic, they pay millions of dollars just merely for hiring people to generate those labels, like those preference data by human labelers. And that's where the Chatbot Arena project comes from. So as you can see from this slide, Chatbot Arena is essentially a slightly gamified data connection UI. And as this slide shows, the UI panel has two sides. So each side corresponds to a chatbot, but with their name hidden from the user. And at the bottom, you can see an input box where user are allowed to type a prompt, and then the two chatbots will provide response at the same time for the user's questions. And the user are then asked to read the response and rate them. And among all, like there are four options given to users to choose. A is better, which means that the left chatbot's answer is better. B is better, the right one is better. Tie, or both are bad, right? So this is basically a very initial phase of the Chatbot Arena project we designed in order to gamify the connection process of humans' preference data, like ranking data between two chatbots. And later we basically populate this platform to many users, and we also collaborate with a lot of interesting companies, including Kaggle and Hugging Face. And we serve the 20 plus models in this website, which shown is on this slide, https chat.lms.org, and you can definitely feel free to try it yourself. It's still online. And we start connecting a lot of user votes to rank different chat assistants. Once we connect enough votes, that ranking that provides this kind of pairwise ranking between two chatbots, we can start drawing some really nice insights from these votes. So at the left side, you can see the win rate calculated between based on these votes. And once we get this win rate, we can do something more interesting. That is, we can use the votes to calculate the Elo rankings of these chatbots, and which will result in the leaderboard on right? This probably will remind you of something like a commonly used, that is the Elo ranking, which is used to rank players in Go or in other football games. Yeah, so, and it turns out that this Wukuna model and Chatbot Arena gets a lot of attention, and our projects get a lot of stars. For example, the LLMs.org project, which supports this Chatbot Arena, gets like almost 30K GitHub stars. And we also developed a serving system, which I will spend the majority of this talk on to talk about, which is called vLLM. And we also get a lot of traffic and a lot of votes from the public. As you can see, we almost serve like 60K user queries every day in our Chatbot Arena. And we also regularly publish this Elo ranking leaderboard for different chatbots, and I think this now is becoming the default go-to place for people to check which chatbots, which this kind of open source models perform best in terms of chat. And because our ranking and the effectiveness of Wukuna, I think a lot of interesting Medium articles are published to say that open source chatbot models is very promising, blah blah blah. Yeah. Well, if you are interested, I can actually talk about the story and the empirical results behind Wukuna and Chatbot Arena for an entire day. But in today's talk, let's shift the focus more on the hardcore system story behind the scene. So the backend system, so this slide basically gives you a sense of the backend system and the deployment of the Chatbot Arena. So in order to connect enough user voting data, we have to serve all those models of users that are interested by users simultaneously in this Chatbot Arena website, while still guarantee high throughput and low latency. But as a small academic group in university, we indeed do not have a lot of compute. So in our setup, we basically only have like 20x A100 40 GB memory. And in the first week, we have to serve the Wukuna 13B model to support all the user traffic. And after the first week, we're gradually increasing the number of chatbots served to more than 20 in order to connect the different votes that ranking the preference of those different chatbots. And we have to sustain an average traffic of 40K per day in average. So how can we develop? Then the problem comes, right? How can we develop a good serving system to support this kind of traffic with limited resources? So this actually forms our main use case. That is, we are providing this public LLM inference service, and we want to connect both to rank LLM models. But and this drives us to think really hard how we can serve these models economically. So let's break it down. Let's write down this problem. So how to efficiently perform inference and serving for autoregressive LLMs, and this is a core system problem that we try to solve here. Okay, and that actually drives us to the main part of this talk. That is, we are going to talk about a major technique that we invented to address this system challenge. It's called page attention. And centered around page attention, we actually implement a full stack of inference system called vLLM. And I will give more context about the system side, vLLM, and the software side. But basically, vLLM now is basically the #1 open source serving system in GitHub community, and it has attracted a lot of users to use vLLM to serve their models. Okay, in order to understand the vLLM and the core technique behind the vLLM, let's first take a look into the inference process of LLMs. So how does LLM compute as inference? So first, the user provides a prompt consisting of multiple tokens. And in this example, the prompt is artificial intelligence is. And the prompts goes through the model, and we get the next token to the prompt. And in the next step, we feed this new token Z back to the model and get a second output future. And this process is repeated until the sequence either reaches its predefined maximum sequence length. For example, in Llama, this maximum sequence length is somewhere at 2K, or it will stop after generating a certain token called an end of sequence token. Right? This basically gives you an overview of how this inference computation looks like. So in the inference process, LLMs have a unique component, which is called a KV catch in the ML literature. So in processing a new token, the model actually needs not only the representation of the current token, but also the hidden representation of all the previous tokens. So these states of previous tokens should be kept in memory, and this is called KV catch. And in this slide, I basically highlight the KV catch of the previous 3 words, like artificial intelligence is. And each layer actually have KV catch. So this KV catch is layer-wise. And when a new token, in this example, the token Z is generated, besides the token itself, its corresponding KV catch also need to be kept and appended to the KV catch memory space. So here in this slide, you can see when we generate a new token Z, we have to append a new KV catch for this word Z in the KV catch space and for each layer. So to recap a little bit, KV catch is memory space to store intermediate vector representations of tokens. While the name is probably a little bit misleading to researchers with a system background, but you can basically think of this KV catch as a working set for a sequence rather than a catch, because the model uses every previous token state to generate the next token. So importantly, the size of KV catch dynamically grows as new tokens are appended, as I have explained, and it also shrinks as the tokens are deleted once the sequence finishes. Okay, with that, we just put the KV catch in memory and we are good. So why do we really care about these catches? And that's the key problem that we try to address in vLLM. So what if I tell you that efficient management of KV catch in memory can greatly improve the LLM serving throughput? So let me try to explain this key insight. So let's say we run a 13 billion LLM on a 40 giga A100 GPU. So the model parameters take roughly 26 giga of memory. And in addition, a small fraction of memory is used for workspace, and the rest of the memory can be used for KV catch, which is denoted as pink area in this figure. And we can have a curve plot where the x-axis is the number of requests, that is number of prompts that can run in parallel in this GPU. And the y-axis reflects its memory usage, which is capped by its memory capacity, say 40 giga for this setup, A100 setup. A key finding is that as we put more requests in a parallel batch, so existing systems use KV catch very inefficiently, and it will quickly hit the cap. Thus, it was significantly limited the number of parallel requests that can be batched together in GPU. So in this figure, you can see when we hit a batch size equal to 8, that is when we try to process 8 requests in parallel, we will hit the memory cap of GPU. So in contrast, if we can have a solution to manage KV cache more efficiently, so we can try to flatten this origin curve into this blue curve, thereby allows larger batch size with the same amount of memory, right? Here we don't change the cap memory of this A100, but we are able to, if we suppose that we are able to flatten this origin curve, we will be able to fit 40 requests in parallel in a batch. Okay, so why we want to pursue this? So this is probably one of the most important slides of my talk. So this increased batch size can directly translate into increased throughput. So if we draw another plot below to illustrate the relation between batch size and throughput, we can see that as we increase the batch size processed in parallel, before the GPU reaches its compute roofline, we can almost observe a linear increase in throughput, right? Which means that as long as we are able to fit more requests in parallel in a batch without hitting the memory cap, we are essentially linearly increasing the throughput. And this linearly increased throughput will translate into like a cheaper serving price. Okay, so what are the memory inefficiencies in the previous systems? So this is a snapshot of the KV cache when using a previous system, where we find three types of memory wastes. The first is reservation, which means the slots that are not used at this moment, but will be used for the sequence in the future. Here, the 3 slots in the middle are reserved because they don't store any token at the current step, but will be used to store output tokens in the subsequent steps during our inference serving. So the second is called internal fragmentation. I think if you have ever taken any operating system, you are familiar with this term, which means that the slots allocated for a sequence but never used. This happens because the output length of a sequence is not known a priori in our inference. And finally, external fragmentation happens because different requests A and B may have different sequence lengths, and this is also a very common problem that we face in operating system memory management. So the memory waste is significant. So in our profiled data with different memory management schemes, we observe that only 20 to 30% of KV cache is actually utilized to store the token states. The rest of the space are just wasted. So in contrast, in our solution, by optimizing the memory management, we can achieve over 96% average utilization of the KV cache space, which is several times higher than the existing system. And this probably will remind you of one of the most important curve I just showed. So basically, by better utilizing the memory, you can increase the batch size, and which will in turn increase the throughput. So that's the core logic behind this work, vLLM and page attention. Okay, now we understand this problem. So what is the secret sauce here? As I already mentioned operating system many times, I believe many of you probably will find that this is actually a very old problem, right? So the way vLLM solves this problem is to employ the old idea of virtual memory and paging in operating systems. So as we all know, OS uses paging to reduce fragmentation in the physical memory space, and uses virtual memory for efficient space multiplexing between processes. And so what vLLM does is basically the same. It uses a similar kind of idea to resolve the fragmentation in the KV cache and enable efficient space sharing between requests. And this is enabled by our technique page attention, and let's dive into it. So to begin with, we partition the KV cache space into an array of token blocks. So a token block is a fixed set trunk of memory that can store token states from left to right. And in this particular example, the block size is 4, which means that we can store 4 tokens, the KV cache of 4 tokens in a block. So to clarify a bit, the tokens here are not strings. So they are token states, the vector representations of the token in a sequence. So for example, in Llama 13B model, each token state would consume about 1 megabyte of memory, and it becomes larger when the model is larger. So on top of this, we introduce the so-called page attention, and our new, which is a new implementation of the attention mechanism. So we find that the fundamental limitation of the previous system is that they require all previous states for a sequence to be stored in a contiguous memory space. And this is conventional in typical DNN workloads where the input and output shapes are static, which are taken by granted in deep learning libraries like TensorFlow or PyTorch. However, it turns out to be highly inefficient for LLM inference, where the sequence lengths are highly dynamic and unknown. And the page attention directly addresses its limitation. And with page attention, the key states can be stored in non-continuous blocks in the physical memory space, and they can be located in arbitrary position in the key cache. So we virtualize the key cache to logical and physical token blocks. So let's see how it works with an example request A. And this request A comes with the prompt, Alan Turing is a computer scientist. So in the logical view, the tokens are stored in consecutive blocks and their orders is preserved. As you can see from the left, they are first, so in the logical view, they are stored in block 0 and block 1. But in the physical view, on the other hand, the tokens in the same sequence may not be stored in adjacent blocks, and the order between the blocks can be arbitrary. And the mapping between the logical blocks to the physical blocks is stored in the block table. So in the figure, you can see the virtual block 0 will be mapped to the physical block 7, right? And the virtual block 1 will be mapped to the physical block 1, which can be queried from the block table. This probably will remind you of all the old techniques used in today's operating systems, that the virtual paging, physical paging, right? So let's continue this example. Let's say the model has generated the next token, and the new token is first appended to the last logical block, which is block 1 on the left. And using the block table, we also append the new token to the corresponding physical block. And this is where the true memory writing happens. That is in the physical block 1 and the third slot of this block 1. We are going to write the key cache for this word, and. And the same for the next new token, mathematician, right? We will do the same thing. Basically, in the virtual block, we store it at the end of block 1, and we query the block table, and we find that the virtual block 1 will be mapped to the physical block 1, and we are going to write the key cache of this new word, mathematician, at the end of the physical block 1. And finally, if the last block is full, then we allocate a new physical block and store the token in the first slot of the new block, which is block 5 on the right. Note here, the block 5 is allocated on demand, so we don't have to reserve any memory. And this will eliminate a larger portion of reserved memory, and this reserved memory space can be used for serving more other parallel requests, like this. So this is basically how vLLM manages the key cache. So far we have covered how it works for a single request, a single sequence. But you can imagine how it's going to work for multiple requests processed at the same time. Just like all operating system virtual memory for processes, we allocate different token blocks for different requests. So let's quickly analyze the memory efficiency of vLLM. So first, vLLM has minimal internal fragmentation. This is because the internal fragmentation only happens at the last block of a sequence. This means that the number of the wasted tokens per sequence is bounded by the block size. And in practice, the block size is much smaller than the sequence length. So in our example, the block size is only 4. Second, vLLM does not have external fragmentation because all blocks have the same size. And third, vLLM does not reserve memory. Like I said, a new block is allocated on demand. So putting things together, vLLM achieves a very high utilization of key cache, over 96% on average. It greatly boosts the memory efficiency compared to existing systems, which will in turn translate into throughput improvement. So another advantage of the dynamic block mapping is that it enables sharing between requests. So for example, if you use Copilot frequently, you are probably familiar with this pattern called parallel sampling, which will generate multiple outputs from the same prompt and let the users to decide which one they want. So in such a case, the computation and the memory for the prompt can be saved and shared between parallel sequences. So page attention naturally supports this kind of pattern using the block table. So when sequence A and B have the same prompt, page attention keeps only one copy of it in the KV cache by mapping the logical block of A and B to the same physical block. And in addition, it keeps track of the reference count of the physical block. So what happens in the next step? So A and B will generate different output tokens from the prompt. Now A and B cannot share the last token block. So this page attention will handle this using a copy on write mechanism. So basically, it will decrease the reference count from 2 to 1, and then it try to copy and write the last block. And it copies the last block to the new free block and appends the new token there, and this decreases the reference count by 1. And this will effectively handle this kind of sharing, because the first block, which maps to the world, the future of cloud, is still shared between these two requests. Right? Then we can process A and B just like before, while keeping the most of the prompt tokens shared between the two. Okay, so basically that's an overview of the core technique behind the vLLM and page attention. And we implement this vLLM as an end-to-end serving system that includes front-end, distributed model executor, and scheduler. And more specifically, vLLM can be thought as an inference engine with custom CUDA kernels. And we use Ray and Megatron for distributed execution. And we open sourced vLLM in June and released the system as a patent package. And vLLM is one of the key techniques that enabled the Chatbot Arena project I just briefly mentioned at the beginning of this talk. And since the release, we have seen like vLLM have been widely adopted across many open source projects and across the industry. And we have also received many open source contributions, as you can see from this slide. Now let's talk about the evaluation a little bit. So the metric we will use is service throughput, and the way we measure it is to find the maximum request rate that the system can serve without exploding the queuing latency. And for synthesizing the request rates, we use two different datasets. One is the shared GPT dataset that I just mentioned to train Vicuna, and the other is the Alpaca dataset used to train the Stanford Alpaca model, which is another very famous open source LLM. And as you can see on both figures, where the y-axis is the normalized latency, which is the mean of every request end-to-end latency divided by its output length. So vLLM, the blue curve, returns much higher request rate than other baselines while maintaining low per token latency. So when we bound the per token latency to 100 milliseconds, vLLM achieves 6 to 13 times higher throughput than fast transformer, and 1.7x to 2x higher throughput than Orca. So Orca is another distributed system for serving LLMs. And we also compare to Hugging Face and TGI. TGI is another state-of-the-art serving engine before vLLM developed by Hugging Face. So we observe that vLLM has up to 24x higher throughput than Hugging Face, and vLLM has up to 35x higher throughput than text generation inference engine by Hugging Face. Okay, in conclusion, the key behind the vLLM and page attention is to modernize virtual memory operating system for memory efficient LLM serving. And the vLLM improves the memory efficiency of LLM serving by 2.5 to 5x by minimizing the memory fragmentation and enable sharing. And this leads to 1.7 to 4x higher serving throughput compared to state-of-the-art. We also note that vLLM is more effective for large models, long sequences, and complex sampling methods such as the parallel sampling and beam search I mentioned. Okay, that basically concludes my talk, and you are very welcome to check our projects and some other open source projects in my lab, including ALPA, ARM-Sys, Org, and vLLM AI. Yeah, thank you.